What's this big secret you can't tell me?
Okay, so what we're
I
looking at here
don't
is
want a piece
special
of
phase
this.
about last time. So here we've got a 20 kg mass, okay, and we want to see what the acceleration is. So acceleration is equal to force over mass. What's the force in this case? Well, it's going to be 20 kgs multiplied by 9.81. Okay, we're going to divide that by the mass. Now this is the tricky bit, is you've got to make sure, actually I think it's 2.0 kgs actually. You've actually got to get the combined mass, so 4 plus 2.0, okay, because the force that is there, okay, from the weight, well, that has to move this, which is a given, but it also has to move this mass as well. So it's got to move two masses. That's a very important thing to remember. So if we work this out, you get 3.27. Okay, this one here, second one, oh, take up that much room there. Second one, a little bit more tricky. Okay, what's the force here? That's an interesting one. So the force there will just be F equals 2 times 9.81. Which equals 19.6 newtons. Okay. Now the tricky bit here is, well, what happens down this slope? Now we need to accelerate a mass here. So I'm going to leave this one with you. I'm going to give you a mass though. Let's put this one here as 1.2 kgs. Okay, to work this out, you need to think about, well, what's the force going down there from the 1.2 kgs. You know the force up this way is 19.6. Okay, and you go from there. Okay, so just like we did before, you find this force here by using your weight, and it's a component of the weight going down the slope. Okay, and then you'll do 15.6 minus that force, and that will give you your resultant force. Okay, and so that resultant force is the force on that mass there. So it's an interesting problem, this one. So looking at Newton's third law, okay, use your dictionary now. This one here is a good one. Whenever a force acts on a body, an equal but oppositely directed force of the same kind acts on another body. Okay. Now note the law implies always in pairs, same kind, equal magnitude, same line, but opposite and always on different objects. So one important one here is, imagine you've got this apple here. It's got a weight force because it's in a gravitational field. But what is its, according to Newton's third law, what's its equal opposite force? Well, it's the weight force caused by the apple attracting the earth towards the apple. Okay, so there's an equal and opposite force in that case. If you slap someone, then the pushing force against someone's face will be the same force as the face pushing against your hand. You've got to match the forces. In this case here, it is two gravitational forces. And in the case of slapping someone's face, it is a pushing force in each case. So you can see here, these are just general descriptions of pushing forces. But you look at the pairs on this book here. So you've got your book. There is the weight of the book is matched by the weight of the earth because of the book. It's always going to be a very small force. okay, but it's equal and opposite to the size of the weight of the book. Then there's a pushing force of the book on the table, and then the table pushes on the book. Okay, so there's 4 forces there, and they're all matched. Impulse and change of momentum. Okay, definition of impulse. Okay, definition, impulse. Okay, definition of impulse is related to this formula here, which is the impulse formula. It is the size of, the product of the force changing the momentum of the object. So it'll be this product of the force and the time for which this force acts against the object. Okay, so that's what that formula says, force times change in time. Okay, from Newton's second law, F equals ma. Okay, so hence what we're going to do here is I'm going to put in a substitute for A. So I'm going to have m v minus u over t, okay, in there instead of A. Now, how do we go from here? Well, impulse is equal to force times change in time, which is equal to in this case, if you think about it, so force, impulse equals force times change in time. And if you have a look at what we've got here, we have got mv minus mu. Now what does that mean? That's just your change in momentum. Okay, so change of momentum. Now, yeah, so now what we have here is a time on the bottom, but remember this part here, what's all that equal to? That's mass times acceleration, so that's equal to force, and we must now multiply that by a change in time. So change in time. So impulse, which is force times change in time, is the same as mv minus mu, and those times cancel. Okay, so impulse is essentially equal to the change in momentum. Now, so we've got an example here. A 600 kg mass has a force of 20 newtons applied to it. If it starts from rest, how long will it take to reach a velocity of 5 meters per second? So that's your final velocity. Got a force of 20. You've got a certain period of time, okay, for how long it's going to accelerate, and a mass of 600 kgs. So how long will it take to reach a velocity of 5 meters per second using the idea of impulse? Okay, so mv minus mu is equal to force times change in time, okay, from what we just did before. So 20 times time is equal to 600 times your final velocity minus 600 times your initial velocity. Okay, so once we work all that out, so 20t is equal to 3,000, so t is equal to 150 seconds. Okay, I've got an example here of a 70 kg rugby player gets tackled in a game. He is running at 7 meters per second before he is stopped by a tackle. Calculate the change of momentum of the rugby player. So what is the change of momentum? Remember, so this is A, change equals final minus initial. Very important, that. Okay, so what's the change of momentum then? So change in momentum is equal to mv minus mu. Final momentum minus initial momentum. So what's his final momentum? Well, 0 minus his initial momentum, which is 70 times 7. Now, be aware that this is now a negative, okay, is a negative. So the change of momentum is opposing the fact that he's stopped, okay? He's got to be a negative momentum to become 0. B, state the impulse in the rugby player. Well, we just know that the impulse is the same as change of momentum, so negative 490. C, if the collision lasts only 0.9 seconds, what is the average force on the player? Okay, so impulse is force times change in time. An impulse in this case happens to be the same size as the change of momentum. So what's the force when we multiply that by 0.9? So force is equal to 544 newtons. Okay, so it needs about 50, 55 kg person to stop him standing on him type force. Force time graph. Now we're going to check this in class. We're going to run something down a ramp, okay, and let it hit a force meter at the bottom of the ramp. So a little car is going to run down the ramp. It's going to hit that thing, and we're going to get a force time graph. Now, if you do it, you might get a graph that looks something like that. Now, some particular points about this graph, okay? We know that impulse or change in, let's do a triangle there, change in momentum is equal to force times change in time, okay? So the area under this graph is effectively force times change in time. So if we work out the area of this, well, what does it equal? Area will equal impulse or the change of momentum. Now, if you extend the time for which something collides for, then the area has to stay the same. Like if you got an object going at 5 meters per second, it's 5 kgs. If you can slow down its stopping time, it's still going to have the same change of momentum. It's still going to go from 5 times 5, 25 to 0. So it's still going to have the same change of momentum. It just is going to be over a longer time. So what happens to the force then? So if I draw a new graph, if I have the same area here but over a longer time, I must then have a smaller force. So that's the idea behind crumple zones in cars. No matter what, if you're going at 100 kilometers an hour, it doesn't matter what car you, doesn't matter how you crash, you've still got the same momentum beforehand. If you're going 100 kilometers an hour and you've got 100 kgs, you've still got the same momentum. Doesn't matter how you crash. What does matter is your impulse. So when you crash, if you crash over a longer time, so in other words the crumple slows you down slower, so the time for which you slow down is longer, then the overall force is smaller. Conservation of momentum, this is essentially directly from your dictionary. Now with this one here, the important thing when we talk about this is what does it mean by isolated systems, okay? So what does a system mean? A system is essentially just all the things that you're looking at in terms of the objects and what happens with the collisions. So the collection of all the forces. So the total linear, oh, what's happened here? Okay, so in this case, the total linear momentum of an isolated system remains constant. Okay, so what does that mean? Well, that means if you have a certain momentum going this way, okay, of an object, let's say it's 3 kg ms to negative 1, and I had another object going this way of 1 kg ms to negative 1. Well, it's a negative because it's going in a different direction, So the total momentum here is equal to 2 kg ms to negative 1. Now that value can't change. If we're just looking at these two objects all the time, that value will stay the same. So if these things crash, some sort of explosion, okay, then afterwards it has to be, the movement of all the particles and so on has to be 2 kg meters per second. So if we take these two cars here and they collide, the only two forces will be the forces on each other, okay? So because of that, then the total momentum is always going to be the same. If the collision occurred with something attached to the ground, so let's say we ran this Ferrari into a wall, then we actually have to take into account the Earth, okay? Because if you ran this Ferrari into the wall, then the Earth would actually bounce backwards a little bit, okay? The Ferrari will probably bounce back a lot faster, but the Earth will actually bounce back a little bit. So what we're going to do is calculate the final velocity of car B if car A travels left at 9 meters per second after the collision. So after the collision, so this car here, let's say is, what's that, is that A? And that one's B, okay. So let's say after the collision, then car A is going to be traveling this way at 9 meters per second. So let's work out the total momentum. So momentum of car A is equal to 15 times 1300. Momentum of car B is equal to negative 20 times 1380. So let's work out these two. So that gives us 19,500 kg ms to negative 1. And the other one, 20 times 1380 is equal to 27,000 27,600 kg ms to negative 1. Okay, so what's the total? Oh, that's a negative. Okay, total will be negative 8,100, okay, kg ms to negative 1. In other words, it is going, the total momentum seems to be going to the left, okay, on general. You can see it, that in this case the Corvette's probably going to win this collision. So if one car is going to the left, what's the momentum of this one? So that means it'll be going 9 times 1300, and that gives it 11,700. Okay, and we need to add up to negative 8,100. In this case, this one must be a negative because it's going left. Remember that speed there must be a negative. So what do we have to do? Well, let's have a look. We need to be going this way with a momentum of 3,600 kg ms to negative 1. So how do we find that then? Okay, so 3,600 is equal to 1380 times a certain speed. Okay, so if we divide this by 1380, we get a speed of 2.6 meters per second to the right. Is the total kinetic energy the same after collision as it was before? Okay, so you can work this out. In this case, no, it's not. Okay, when you work out the total kinetic energy, so energy is lost, but momentum is not lost. Okay, so in this case here, we're bouncing a ball. We've got a ball going down at 8 meters per second, and then it bounces up at 5 meters per second. Okay, it's 150 grams, so it's 0.15 kgs. Okay, so how do you work this one out? Total momentum before. So momentum of this one, let's call it 1, will be 8 times 0.15. that equals a certain number. What's the momentum of this one? This one's going to be -5 times 0.15, and that will be a certain number. So what you're going to do then is find the total, the change. So the final, which will be P2, P1, so change of momentum equals P2 minus P1. Okay, that will be your change. Don't forget the negative. Is the momentum conserved? Well, in this case, we actually do get a change. We do get a change. So what are we missing? We are ignoring the Earth. Okay? We forgot that the Earth here actually comes towards the ball as the ball's falling towards it, and then it bounces away from the ball as the ball's bouncing away from it. When you have explosions, the total momentum of an object at rest is 0, so afterwards the total momentum of an object must also be 0. Okay? So in all these cases here, the total momentum afterwards has to be 0, which is the same as before the explosion. And so you can do that here. Okay? If B has a velocity of 30 meters per second to the right, and it's got 30 kgs, so that's about 900 kg EMS to the -1. The left also has to be 900, so that means it must be going a lot faster, in other words 90 meters per second, after the collision. So on the last one here with the cannonball, okay, the cannonball will be essentially what's total momentum here is 0. So afterwards must also be 0. So if that cannonball moves to the right at 90 and it then must have a total momentum, you multiply it by the mass of the cannonball, there must be the same momentum of the cannon going that way. Okay? So you work it out back the other way. There's two types of energy considerations of collision. One is elastic, one's inelastic. You see the dictionary, elastic. Momentum's conserved, but kinetic energy is as well. Inelastic, momentum is conserved, but kinetic energy is not conserved. And you should be able to work out these ones now. And all you've got to say is if kinetic energy is not conserved, then it must be inelastic. If it is, it must be elastic. End of part 2.
So what's this big secret you can't tell me? I don't want a piece of this. Haven't we all had enough?